Hello and welcome. You are looking at the Geometry Spring Final Exam Video Review. And this is the final video that I will also be recording for this year. I'm going to be covering 24 textbook problems that were requested by you, the students. Five of them, 5 are from Chapter 6, about 15 from Chapter 10, and 4 from Chapter 11. It adds up to 24 problems there. Now there are 2 chapters that are not being covered in here specifically by problems. However, Chapter 8 on right triangles will be recognized here in Chapter 10 and in Chapter 11. Chapter 12 is not recognized here. Chapter 12 was on circles with the tangent lines, the secant lines, the inscribed angles, the central angles, the graphing circles on the coordinate plane, stuff like that. There is a video, however, that's on that. Just find the one that's titled some circles review, I think. Something like that. Anyway, these will be going in order. I'm going to start with Chapter 6 and then go on from there to Chapter 10 and Chapter 11. And let's see how long this one lasts. So from Chapter 6, on quadrilaterals, this is problem number 25 in section 6.1. I really should make mention of that somehow, which one it is, if I can remember. In each figure, find the measures of the angles and the lengths of the sides. So it's just one figure here. It's an isosceles trapezoid DEFG. Now, they mark up almost all that you need for this. I almost wish they didn't do that. If they give you that it's an isosceles trapezoid, there are some things you should know yourself. For example, and this one's not marked up, but I don't know if it matters, these are parallel to each other. It's one pair of opposite sides that are parallel. The non-parallel sides that are called legs are congruent to each other. There's the markup there. So just to start by solving for one of the variables here, if these two legs are congruent, then a minus 4 and 11 have the same length. Solve for a, you get 15. So if a equals 15, then we substitute 15 everywhere for a. 2 times 15. Now, I don't think, they didn't ask you to, oh, yeah, they did, lengths of the sides. There we go. I was like, why would we solve for a, and why is a all around here? I guess we got to solve for the lengths of the sides. EF is 15. ED and FG are both 11, and DG apparently is 2 times 15 plus 2, which is 32. These are all just units. They don't say anything about centimeters or inches or feet or anything like that. Okay, now it doesn't look like there's a B here, but there is a C. Here's C degrees, and here's 4C minus 20 degrees. Now, base angles are congruent to each other, so angle D is congruent to angle G, and angle E is congruent to angle F. And also, if there's something else that you must know about this thing, with these two sets of lines being parallel, then these two angles are supplementary. So if I add up angle D with angle E, I will get 180 degrees. Now, E and F are congruent, so E also can be represented as this expression here. So if I add up the measure of angle D with the measure of angle E, or F, in fact, here, let's just put F, it's going to equal 180 degrees. Substitution, C is for D, 4C minus 20 is for F, and that equals 180. And 5C minus 20. All right, so C is going to equal 40. So C is 40, so as far as the angle measures that we can figure out here, it's going to be measure of angle E is equal to the measure of angle F, which is going to be 4 times 40, that's 160, minus 20, which is 140 degrees each. Measure of angle D and measure of angle G are equal to each other, and they are exactly 40 degrees. So if you want to confirm this one, if you add both of these 40s, 40 plus 40 is 80, and 140 plus 140 is 280, 280 plus 80 is 360, and that's what should happen in all quadrilaterals. Their interior angle sum, as well as their exterior angle sum, actually, should be adding up to 360 degrees, and it does. All right, this one, I believe, is in section 6.2. Find the values of x and y in parallelogram PQRS. Now, this problem I kind of appreciate more with respect to what they hide from us. You want to know the definition and properties of a parallelogram, and in doing so, you're going to have to figure out what it is that they give you and what you need to find out. So in a parallelogram, the one property with the diagonals that they drew here you're going to use is that diagonals, they're not congruent to each other, but they bisect each other. So that means that segment PT and TR are congruent. Okay, and if they're congruent here, you can see that PT is 2x and TR is y plus 3. So 2x equals y plus 3. Those are both equal to each other. Furthermore, we have QT, and that's congruent to TS. So now that we have expressions written for these two here, 3x and 2y, we know that these two are also equal to each other because PR bisected QS at t. So 3x equals 2y. So what I'm going to do here is actually write this as a system of equations. Let's get these together here. There we go. System of equations here, and we got to solve for x and y. So there are a lot of different options that you have here, and this can be a very large algebra talk. I'm going to try and do the best I can and narrow it down into, I'll do one way through substitution for you and one way using elimination. That sounds fair. If I take this equation here and I isolate my y variable by subtracting 3, I'm going to get y equals 2x minus 3. And if I take that 2x minus 3 in place of y in this equation right here, then I'm going to get 3x equals 2 times 2x minus 3. Now you can distribute and solve for x. 3x equals 4x minus 6. Subtract 3x over here, add 6 over here, you're going to get x equals 6. So there's your value for x, and in solving for y, now you can just substitute what you found for x in for this equation over here. Y equals 2 times 6 minus 3. 12 minus 3 is 9. So your values of x and y, if I wanted to write it as an ordered pair, I suppose I could. It would be 6, 9, like that. Otherwise, you have your answers there. They did not ask you to actually find the lengths of these things, but to confirm it and to make sure it makes sense, let's see if PT and TR are congruent. Well, x is 6, so PT would be 12. 9 plus 3, right here, TR is 12 as well. 3 times 6 is 18. 2 times 9 is 18. All right, so everything checks out there. So that's one way of solving it, using the substitution method by isolating a variable first, or something that you can liken to the other equation as a term and substitute it there. Another way is using what's called the elimination method, and what I'm going to begin by doing is rewrite the original two equations I had here, 3x equals 2y, and 2x equals y plus 3. Okay, there are a lot of ways to go about this. Most people's comfortableness in doing so is getting their x's and y's on one side of the equation as to eliminate, and then getting any constants on the other side. So for both these equations here, for my first one, I'm going to go ahead and subtract 2y next to 3x. So I'll get 3x minus 2y equals 0. And I'm going to go ahead and subtract y over in the second equation here. And I'm going to get 2x minus y equals 3. There's no real reason for me to do that other than whenever you do elimination, for the most part, you see it in standard form like this. You know exactly where everything's lined up, and you don't make a mistake of subtracting where you weren't supposed to. Or at least that's a good preventative measure that you take in doing so. So the elimination method, I'm not going to describe the whole reason behind how or why you can actually add down the list here. But as long as I'm combining like terms and they're on the same side of the equation, I could actually be adding these things up like so. Now, the problem with doing this is I didn't eliminate a variable. So adding straight down does not work unless you have x's that are additive inverses of each other or y's that are additive inverses of each other. So what I want to try and do next in this thing is take one or two of these equations, but it looks like I can eliminate y a little more easily than eliminate x, because either to eliminate x I have to multiply or divide by a fraction, or I have to multiply or divide by both equations here. But for this equation here, if I multiply this bottom one, say by -2, what you're going to see is a change in this equation where instead I get -2 times 2x is -4x. -2 times -y is positive 2y. Now you can see these additive inverses here in play. And -2 times 3 is -6. And don't forget to multiply the -2 with this side of the equation as well. That tends to get lost as an art form. All right, negative 2y plus 2y is 0. Those cancel out. 3x minus 4x is negative 1x, and 0 minus 6 is negative 6. So the opposite of x is negative 6, and as you know, then you would get x equals 6. From there, you take your 6, and you can either substitute that into one of your original equations, like one of these two, or you can go back and you can eliminate x next time to solve for y. That's fine. I just feel like that would take a little too much time at that point. Most people prefer elimination method, though, unless something's already set up for substitution method, such as this problem. And I'm just saying by most, I just mean from the classes that I've taught where they've done it. I've taken hand polls, or when they have an option, you can just tell which one they tend to go for. Maybe just less fraction work and less distribution practice, especially with negative numbers. All right, and that was number 17 on section 6.2. Now we're looking at number 47, and let me actually check which one this is in. Section 6.2, number 47. Find the values of the variables in each parallelogram. Now this looks a lot like the last problem we just did, almost down to the wire of, look, it's 2x and 3, well, last time I think it was 3x and 2y, but look, it's a parallelogram, diagonals bisect each other, just more systems of equation practice. That's fine. So if diagonals bisect each other, then x plus 8 is equal to 2y plus 5, and of course 2x is equal to 3y. So this is one of those ones. Again, I can do both elimination and substitution. Let's go ahead and do that set of practice at least one more time, because I don't think we have any or many more systems of equations problems after this. So let's go ahead and do substitution first. If you noticed last time, I went ahead and isolated this y variable. Now you have a choice of 4 different variables for which you choose to isolate. Either the x on top, y on top, x on bottom, or y on bottom. Same thing here, x on top, y on top, x on bottom, or y on bottom. And the thing that I normally think about is, well, you see with this 2y, this 3y, and this 2x, I'm going to have to divide by this number 2 or 3 or 2 at some point. This x right here has a 1x. I don't have to divide by anything. Now, it's not a problem to divide by something, except for being one extra step. However, it is a problem for all of these because no matter which one of these you divide by, you will end up with a fraction somewhere on the other side of your equation. And that won't give you a wrong answer. That'll just make your work a lot harder to do. So what I would choose to do is isolate this x. I'd say it's the easier one because it only takes one step to get it all by itself, and you have no fractions to deal with. It's perfect. So x, if I subtract 8, equals 2y minus 3. Now I get to take this 2y minus 3 and substitute it in for x up in this equation here, the other equation I have not yet used. That'll be 2 times 2y minus 3 equals 3y. Distribute 4y minus 6 equals, this looks like the same answer as the last one we just did. Negative y, except the opposite effect. Subtract 3y and add 6. We're going to get y equals 6. Yeah, you're getting the same answer the opposite way. I wonder why both problems were independently requested. I should have looked harder into this. Okay, y equals 6. Let's go ahead and substitute 6 for y into this equation here. X equals 2 times 6 minus 3, which is 12 minus 3, which is 9. All right, so 9 and 6. And if you wrote it as an ordered pair, it would be 9, 6. Okay, that was substitution method. And like I said, it looked the exact same as the last problem we just did. So I'm not complaining. I'm very shocked by the fact that 2 problems in the same section were written like that. All right, if I were to do elimination method here, let me rewrite the top equation here where I subtract that 8, but I'm going to subtract the 2y back over on this side. X minus 2y equals negative 3. And the bottom one, I'm going to subtract this 3y over, so it says 2x minus 3y equals 0. Okay, to not make this look exactly the same as the last one, I'll show you an instance of when you want to try to, or not when you want to, but when instead, like let's say I tried to eliminate y here. Okay, I would have to multiply negative 2 by a number to become positive 3. Now that number would be negative 3 over 2. So as you can tell, that would leave me with a fraction here and here, so that's undesirable. But what I could do is find a common multiple of the numbers 2 and 3, which is 6. And I could multiply these equations by the value that will get 6 for both of them. Or in this case, maybe 6 on top and negative 6 on bottom. So if I multiply by a negative 3 on top, if I multiply by a positive 2 on bottom, that would line up my y's in such a way that I will now have, what do you call them? Additive inverses of each other here. So negative 3 times x Negative 3 times negative 2y. Negative 3 times negative 3 gives me that from the top. The bottom, I have 2 times 2x. 2 times negative 3y. 2 times 0. So now you can see how I set this up, where I'm now able to eliminate these two because of what I chose to multiply by. It's a practice you'll have to carry into your next algebra class that you take anyway. So you get x equals 9, and once again, if I carried on, I can get y equals 6 by doing some sort of substitution from any equation of my choosing. But just showing you substitution method, elimination method, how it applies, and in this case, it was from the same setup and same reason. You had diagonals bisecting each other, which is true in every parallelogram. Okay. This is from section 6.5. This was on kites and trapezoids, and this particular problem right here is on a kite. Find the measures of the numbered angles in each kite. So the measure of angle 1, measure of angle 2. All right, so you have some options here and some things that you can work on with this, but the main thing for kites that you want to understand is how these guys are congruent to each other. Let me kind of break down what other thing we can find out based on that. If I drew I need a different color. If I drew a diagonal from this through this right here, I've created two congruent triangles because this is congruent to itself by the reflexive property. So this triangle is congruent to this triangle by by side, side, side. The side, side, side congruence property. Now, if that's the case, you can see that these kind of reflect across each other. Here's a reflection. Here's a reflection. So this too will also be a reflection. Angle 1 and angle 2 are congruent angles by CP/CTC, if you look at it that way. So something that's true about kites is they have some unique things in that there are two unique pairs of congruent segments, sides. They are adjacent to each other. They are not opposite each other. Opposite sides are not ever parallel. This diagonal bisects these angles, and this diagonal right here. However, this diagonal does not bisect this diagonal or these angles or these angles. So there's a unique thing about that. And then the next thing is that while these two angles are not congruent to each other here, these two angles are congruent to each other here. So the kite is very, very unique and interesting in that set. And that's where we just saw this one here. Now, why does that matter? Well, because that means that if I assign a variable to them, it can be the same variable. Let's say it was x. Both of these are x, and in a kite, there are 4 interior angles, and they add up to 360. So if I add 90 with 46 with the two x's, I'm going to get 360 degrees. Okay? And that's where we solve for the rest of it. 136 plus 2x equals 360. Subtract 136, 2x equals 224. And x equals 112 degrees. So the measure of angle 1 is 112 degrees. The measure of angle 2 is 112 degrees. They are both congruent, and that's a valid way of solving for them. Can't really think of many other ways, actually, beyond that. Okay, the last one in Chapter 6 on quadrilaterals, find the value of the variable in each isosceles trapezoid. Here's one. They tell you it's isosceles. The legs here are congruent. Base angles here are also congruent. This is actually a very quick problem. Angle S is congruent to angle R, so the measures are equal to each other. That means 60 degrees is equal to 5x. Divide by 5, you get x equals 12. Not 12 degrees. This is 5x degrees already. You just multiply it by x, and that's what you end up getting. That's it for the problem. There's nothing beyond that I really should or would want to talk about unless you had to find out all the other angle measures. If you did, these are both 60, then that's 120 total. The rest add up to 360, so these are 240 each. So it's 120 and 120. Yeah. All right, these next chapter here is with areas. We have to find the value of h for each parallelogram. Now I'm looking in chapter 10. I think it's section 10.1. And in doing so, well, we have to determine what the area of a parallelogram is and use that to find h. So the area of a parallelogram is base times height. Now that sounds very straightforward. Well, there are two things you have to know. First of all, height is always perpendicular to its base. So if we're talking about this height here, then this is the base. And secondly, the base to which we're referring has to be one of the sides of our parallelogram. So whatever side I choose, like this one right here, okay, well then its height is like that. Now, this height is the same as this height out here. This is why they extended it. So this is also 0.3. I could have also chosen, which I'll go back to that one, but I could have also chosen this one right here, and then its height would have been perpendicular to it like that, and that's h, just like this one is. And so you can see that as long as you have any length of your choosing, you can go ahead and get the height from it. So first I'm going to find the area of this parallelogram using that 0.4 right here, this base length, and this height right here, 0.3. Height is perpendicular to its base, so this area is 0.4 times 0.3. 0.4 times 0.3, I believe, is 0.12 square units. So why does that matter? Well, because I can rewrite the area of this parallelogram using any other base and height. How about this base and this height? 0.5 times h is also the area of the parallelogram. So that's also this number right here. When I multiply 0.5 with h, I should be getting 0.12. Base times height of a different variety there. And I divide by 0.5 from both sides. This is 0.12 out of 0.50. Actually, I don't know what that is off the top of my head. Is it 4 point? Yeah, something. 4 point something. 4.2, I don't know. 0.12 divided by 0.5. Oh, duh, you're multiplying by 2. So h here is 0.24 units. So 0.5 times 0.24 gives you what 0.4 times 0.3 gives you. That's 0.12. That's your area. So this is the height this way. Number 16, find the area of each rhombus. So a rhombus has all sides congruent. Diagonals are perpendicular bisectors of each other. So what does that mean? This guy intersects with this guy at 90 degrees, and it breaks these up into equal parts. Now the original diagonal they had, this one that was 6 meters, means that this is 3 meters here, 3 meters here. We don't know how long this one is. Diagonals are not congruent to each other unless this was a square. Make no assumption of that. Let's call this x for the time being. Well, we have here some right triangles like this one down at the bottom. X is a leg, 3 is a leg, 5 is the hypotenuse. So this is a 3, 4, 5 special right triangle. Let me redraw this one more time here. 3x5. And if you didn't believe me with the 3, 4, 5, go ahead and try it for yourself. A squared plus b squared equals c squared. X squared will give you 16. And take the square root, x gives you plus or minus 4, but because we're talking about distance, it's just going to be positive 4. So there's x. Now, why am I doing all of this? Because I have to find the area of this rhombus. And the area of a rhombus can be found one of two ways. There's only one way which I can do this one based on the information that I have, and it has to do with the diagonals here multiplying together with each other. Much like a kite, the area of a rhombus is taking 1/2 the product of both of your diagonals, the entire lengths of them. Now, I've done some proofs with that before. It's true for both the rhombus and the kite. There's another way you can do area of rhombus, and that's base times height. The problem with this one here is that even though I know all the base lengths are 5, I can't quite figure out what this height is right here that's perpendicular to it. Because this perpendicular thing is not exactly right here, otherwise this would be a square. It goes up a little more this way, it seems. So I can't be using base times height, or at least with my current information I have, it's probably not wise to do that. I could get angle measures and actually figure it out, but let's save that. Let's use this one here. So if x is 4, that's half of this other diagonal here. The full diagonal, therefore, is 8 meters, like so. And this one was 6. So you could call like D1 is 6 meters, D2 is 8 meters, and the rhombus will be exactly half the product of those two diagonals together. So the total area is 1/2, 6 times 8. So that's half of 48, which is 24 square meters. And there's your rhombus. If it helps at all, when I talked about the proof, diagonal 1 is equal to the height of a rectangle that circumscribes the rhombus, and diagonal 2 represents the base length of a rectangle that circumscribes the rhombus here. So the area of this rectangle would be base times height. It would also be d1 times d2, right? This rhombus takes up exactly half of every quadrant within here that you can see. Half, 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 half. And all halves of this whole means the rhombus takes up exactly half of that area, d1 times d2. There's your explanation again. Okay, coordinate geometry here. We got to find the area of these two guys here, 26 and 27. QRST. So, I don't know if one's easier than the other. The thing is, both of these, first of all, you have to figure out what kind of shape this is. I know you can assume, possibly, but that's not something you'd like to do. Let's first prove that this is what I think it might be. Okay, now when I said that, what I mean is that you can make an assumption of what you think it might be to get started on saying, how do I want to prove it is what it is? Well, one thing is that I could if I can prove this is what I think it is, which is a kite, then that would mean that QT and TS are congruent to each other. Okay. Now Q is at the point 0, 3. Oh, and then SR is congruent to QR. So Q is at the point 0, 3. T is at the origin. S is at the point 3, 0. And R is at the point 5, 5. So these are actually countable up and down right here. This is 3 units. This is 3 units. So QT is congruent to TS. This right here, this unknown length, is the hypotenuse of this right triangle right here with the lengths, with the leg lengths 2 and 5. This one right here is also an unknown length, but it is a hypotenuse of this right triangle here with the leg lengths 2 and 5. So you better believe that 2 squared plus 5 squared equals 2 squared plus 5 squared, or the square root of them, which will give me those numbers. So I don't care what they are, but now I do know that they're congruent, and that's going to be helpful enough from there. So these two are congruent, these two are congruent, this is a kite. So if it's a kite, let's find the area of a kite the way that we know how to. Now I know that you might be looking at this and saying, you know, it would be nice if we just found this area of the square and then the area of these two. Yeah, I'd agree. But this triangle is not really conducive to finding the area of, or this shape right here. That'd be kind of tough to do. So I'm going to find the area of a kite the way I know how to find the area of a kite, and that's doing 1/2 d1 times d2. So we have to find the lengths of our two diagonals. Now that's going to take some work. We have to find this length here and this length here. Okay, actually that's not going to take as much work as I thought it would. I was thinking about Pythagorean theorem. Let's do these one at a time. If I find the length of TR right here, it's going to be the right triangle. It's going to be the hypotenuse of a right triangle whose leg lengths are 5 and 5. Well, this is an isosceles right triangle, which also means it's a 45, 45, 90 triangle. And in a 45, 45, 90 triangle, then this is 5 to 5 to 5 root 2. So the length of TR is 5 root 2. I could have used Pythagorean theorem, but didn't really need to. Right? I could avoid that as well. Okay, finding the length of the other one, QS, same thing, in that it's an isosceles right triangle. Why? Because TS is 3, QT is 3. So this is a right triangle here with 3 to 3 and a 45, 45, 90. QS is 3 root 2. So now we have the lengths of our two diagonals. They are perpendicular to each other. And one thing I want to touch on in case we don't get to see it ever again here is that the diagonals are perpendicular to each other besides knowing that it's a kite, also because these slopes are opposite reciprocals of each other. TR's slope is 1/1. That I just wrote it too. Is 1/1. And then QS's slope is negative 1/1. Opposite reciprocal. Switch the sign, change these two, which they don't really change. It's 1 and 1. So we also know that, so we know they're perpendicular. That also helps us out when we do our stuff here. So our two diagonals, d1 times d2, are 5 root 2 times 3 root 2, and we're going to take half of that. So our total area will be 1/2 of 5 root 2 times 3 root 2. Now, to some people, you're not truly even out of the hole. Some people have trouble multiplying these together. See if this helps. 5 times 3, 15. Root 2 times root 2, 2. Half of 2 is 1, so your area is 15 square units. And that's the area of your kite. Okay, this next one here is a rhombus, and as I said for a rhombus before, there are two different ways to find area, either just like I did with the kite, d1 times c, 1/2 d1 times c2, or doing base times height. And to do that, once again, like I said before, you'd have to know not only what the length of this is here, but what the length of, say, something like this is that goes perpendicular to it is. And that's going to be a little tougher than you might imagine. There are ways to go about it, but that would take a good long amount of time. It looks like if we find the lengths of these two kites here, of these two diagonals here, then we're going to know it is either a rhombus or a kite. Now, I did make mention that this is a rhombus just through assumption. I shall not do that. I shall prove that it is a rhombus first by proving these legs, or these lengths, are congruent here. Now, you don't actually have to figure out what the lengths are. You just have to prove they're congruent by doing, remember, like I said here, right triangle, hypotenuse. Okay, what's the leg length here? 4, and this is 1. So if all of these have leg lengths of 4 and 1, then you know that all these are the square root of 17, the square root of 4 squared plus 1 squared. So I don't need to actually calculate them if I can get 1 and 4 for all these, which it looks like I will. Okay, 1 and 4. So there you go. So this is a rhombus just by virtue of between point to point, they're all the square root of 4 squared plus 1 squared. They're all the square root of 17. Now again, I did not actually have to compute that on paper to prove that. So this is a rhombus, all sides congruent. Diagonals are perpendicular bisectors of each other, so let's find the lengths of both of these diagonals here. Start with this one. Okay, from Q to S, if I went all the way over and all the way up, this is 1, 2, 3, 4, 5 over. 1, 2, 3, 4, 5 up. Hey, 5 root 2. We're back. QS is 5 root 2 this time, though, not TR. All right, get those out of the way. Let's do the other diagonal. From T to R here, we're going 3 over and 3 up. We've done this before. Only it was the different legs. TR is 3 root 2. So, what's the whole take-home message behind all this? These guys may look different, but their areas are exactly the same. The area of this one, 1/2 d1 times d2, is 1/2 5 root 2 times 3 root 2, once again. And we're getting back to 15 square units. So these guys might look different. No, no, no. They are the exact same in area, at the very least here. This thing kind of shifted a little differently than this one. But yeah, same thing. Find the area of each regular polygon with the given radius or apothem. If your answer is not an integer, leave in simplest radical form. So I may still give you the decimal approximation afterward, just to give it to you. However, always try and get your final answer in exact form before you do anything else. Okay. Number 14, you have so many options on how you want to go about this. So I'll try and give you a few to work with. This is a square. Now in a square, the area is base times height, side squared. If I get the measure of only one side, I can square that value, and it's a square. And I know it's a square because they call it a regular polygon, and it's four-sided, and a regular quadrilateral is a square. So, way number one to go about this. One radius is congruent to the other radius. This is 6 and 6. The central angle of a square is 360 divided by 4, so it's 90 degrees. So this is 6 and 6, as we just said. This is the hypotenuse for this right triangle here, so this would end up being 6 root 2. So if this is 6 root 2 and this is the length of one side, then the area of the square is 6 root 2 quantity squared, which is 36 times 2, which is 72 square centimeters. There you go. So that's one way of going about this problem. Maybe it's even the quickest one. All right, second way. You have a radius of 6. let's draw down an apothem that will bisect not only the central angle from 90 to 45, but also this side length right here, which is going to, if this was x, then the whole length here is 2x. Fine. In a 45, 45, 90 triangle, if this guy here is 6, then we got to figure out these lengths here, one or the other, by dividing, and I'll call this one A. I'll do kind of two ways in one, because they're both the same length. Dividing 6 by the square root of 2. So, if I take 6 divided by the square root of 2, I'll get x. Now, I'd like to write this in simplest radical form to begin with, which means I must rationalize this denominator. Okay, I do not want a radical in the denominator here. So I'm going to multiply by root 2 over root 2. That's going to give me 6 root 2 all over 2, which is 3 root 2 centimeters. So that's the value for x and for a, by the way. Your apothem and half a side length are both 3 root 2. I'm going to save the apothem one for later, if I can. There we go. Save that for later. So x is 3 root 2, right? So 2x, the length of one side, we're back to 6 root 2, and you get to do with what you want to do with it. Square it, and we get this once again. All right, a third way of doing it is using that apothem, here, 3 root 2. We'll do the area of any regular polygon, which is 1/2 AP, apothem times perimeter. Let's get the perimeter of this square by taking any side length, like this one here, and multiplying it by 4. 4 times 6 root 2 is 24 root 2. So area equals 1/2 apothem times perimeter gives you half of 3 times 24 is 72. Root 2 times root 2 is 2. Half of 2 is 1. And you're left with just 72 once again. Final way to go about this problem, well, I'm sure there are even more than this, but a final way to go about this problem is you know that this is also a radius over here, and that should also be 6 centimeters. So this full diagonal in total is 12 centimeters. And as we know with a square, sides are congruent and angles are right. So we are now looking at a 45, 45, 90 triangle that's even bigger. With a similarity ratio of 1 to 2, it's twice as long than the smaller right triangle I was looking at. So in this case right here, once again, if you want to find a side length, it's root 2 times smaller from the hypotenuse to any side length. So if I call this x right here, then x is 12 divided by the square root of 2, which if I multiply by root 2 over root 2 will give me 12 root 2 all over 2, which is 6 root 2 centimeters. So now that your x is 6 root 2 centimeters, take it, multiply it by itself, and one more time, you get 72 square centimeters. So 4 different ways to do the exact same problem, all really based on the same concept. You have to use 45, 45, 90 triangles, which seems to exist in the square quite a bit. And that's actually why people are very comfortable with it, because it seems to be very consistent no matter where you go with it. Okay, here's a regular hexagon. And it's actually drawn a little bit more rotated than I like for it to be. Normally I like to look at them like this. That's just me being picky, because I like for my bottom to be the apothem. But even more so, I'm not even going to draw it like that. I'm just going to go ahead and draw right down here the 3 bottom ones right here. My radius is 6 root 3 meters from my center. So that's this. Okay, the apothem, A, is something that will probably be good to figure out. Now, within a regular hexagon here, your central angle from here to here is 360 divided by 6 degrees, which is 60 degrees. Half of that, as the apothem bisects this angle here, gives you 30 degrees here. So you're looking at a 30, 60, 90 right triangle. Now you have the radius, and you need to get the apothem and I suppose the perimeter, right? Or at least this length right here. Let's call it x again, just this small part. So in a 30, 60, 90 triangle, without using any trig just yet here, 6 root 3 is twice as large as the shortest side, the one that's opposite 30. Hypotenuse twice as long as the shortest side. So if that is 6 root 3, then x is 3 root 3, half of 6 root 3. And it was meters. Your apothem is root 3 times larger than x. So if we take 3 root 3 and multiply it by root 3, that'll be 3 times 3, which is 9 meters. So 9, yes, 9 is less than 6 root 3, by the way. But there's your apothem there. 9 meters. This right here is 3 root 3. So now you have options. I'll just do 2 ways from here. Either you find the area of, let's say, this whole triangle here, and then you multiply it by 6, because there are 6 congruent triangles within this regular hexagon that all have that same area, like that. So if x was 3 root 3, then doubling that amount, 2x, the length of one full side is 6 root 3, which starts to make sense. So here's another way actually that you can think about it here. This triangle is actually an equilateral triangle. It's 60, 60, 60. So look, this is 6 root 3. Oh, this is 6 root 3 too. So you didn't need to know any of that, but you did still need to at some point find out this height, I suppose, unless you used 1/2 AB sine theta. I'm going to ignore any of that for now. So the length of this whole side here is 6 root 3. So if I found the area of this one triangle that's green and red, this equilateral triangle right here, I would do 1/2 base times height. Okay. Now the base is 6 root 3. The height is 9. So half of 6 root 3 times 9 is 27 root 3 square meters. So that's the area of one triangle. The area of the entire regular hexagon then will be 6 times as large. 6 times 27, I think, is 162. It's 162 root 3 square meters. And that's your final answer. They did ask you to leave it in simplest radical form, so there it is. If for whatever reason you decided instead to round to the nearest tenth, like I'm going to right now, it would be about 280.1. I'm sorry, 0.6 square meters, like that. Okay, that's one way of doing this problem. And the second way of doing this problem, it doesn't involve much more than what I just talked about. Well, actually, a second way of doing this problem was doing the equilateral triangle thing that I just mentioned. That was actually a cool way of going about it, now that I think about it. A third way is, instead of using the area of the one triangle and multiplying by 6 triangles, we use 1/2 AP, just like we did for here. We already have the apothem. We're going to get the perimeter in just 1 second. Okay, so the apothem was 9 meters right here. Okay, perimeter is 6 of these, not these guys, 6 of these guys right here. 6 times 6 root 3, which is 36 root 3 meters. So we have 9 meters, 36 root 3 meters, multiplying them, and then taking half of that. Let's go ahead and do that. Area equals 1/2. Apothem times perimeter. Half of 36 is 18. 18 times 9 is double that of 9 times 9, so it's 162 root 3 square meters. Once again, back to where we were. All right. So alternative ways to do this, all depending on what you have. The reason the drawings are so important is because of how you're going to use them, not just memorizing the formulas from there. Hope that there was helpful. The figures in each pair are similar. Okay, this is section 10.4, ratio of area. The area of one figure is given. Find the area of the other figure to the nearest whole number. So at the end, eventually we're going to be rounding it. Okay, so here's the way that this thing works, and I'm going to do a couple things with this. I'm going to recreate this guy. What you're seeing are 2 similar parallelograms. I assume they're parallelograms. They're close enough to be them. I'm not going to actually calculate the area of one or the other. What I'm going to do is be able to find the area of one by knowing the area of the other. So I know that this here parallelogram has half a side length compared to this here parallelogram, which you might then say that this parallelogram is half as large as this one, or this one's double the size of this one. Maybe, but not in terms of area. In terms of area, the question really is, how many of this parallelogram can fit in this parallelogram? It takes 1, 2, 3, and 4. Go figure. What you're doing is you're doubling this side length here, and then you're doubling this side length here. So you're doubling twice, which is multiplying by 4. So it makes sense that if I know the area of one of them, I can get the area of the other one by doing something in that matter. The area of the smaller parallelogram is 6 square inches. So the area of this larger parallelogram is 4 of these guys together. It's kind of bouncy off the thing. I don't really like that red anymore. And 6 times 4 is 24 square inches. So that's the area of the larger parallelogram. And that is rounded to the nearest whole number already. Now that's one way of doing this problem if you have the smartboard tool and you want to use the infinite cloner and stuff like that. That's just the conventional way of me talking about it. Now I want to do some different explanations. Some less conventional ones, or some more conventional ones with regard to how you're probably supposed to approach the problem. And then even a very last one that'll be probably nice for you to try. All right, so the similarity ratio is from small to large is 3 to 6, which means reducing to 1 to 2. Meaning wherever you see 1 inch here that's measured anywhere, here that where it corresponds to will be 2 inches long, or 2 units long of whatever length you're talking about, because it's twice as long in every direction that it goes. And this goes this direction and this direction with regard to the two-dimensional directions. So that's similarity ratio. Now similarity ratio, if it's A over B, area ratio is A over B quantity squared, which is A squared over B squared. Now we just did that before. Let's do it again. Area ratio here is 1 over 2 quantity squared, which is 1 squared over 2 squared, which is 1 over 4. So if the area ratio is 1 over 4, what you want to do is compare the ratio, compare this ratio to these two areas here. Now you don't know this area here. You do know the area of the smaller parallelogram is 6. So I took the ratio of areas from small parallelogram to large parallelogram. Oh, they do tell you it's a parallelogram. Then I want to compare it to the true area of the small parallelogram to the unknown area of the larger parallelogram. Cross multiply, you're going to get x equals 24 square inches once again. So this still applies in that same way. You're finding it with a more mathematical mindset with it. Just understand that the area of this is not 12 square inches. It is 4 times as large, not twice as large. Third way of doing this problem is by keeping the similarity ratio 1 to 2. If we know that the area of this is 6 square inches, we know that's a result of doing base times height, 3 times h. If 6 square inches is done by multiplying 3 with an h, that means your h value must have been 2 inches. Okay, so if this is 2 inches, remember similarity ratio, this length must be double that. So this length is 4 inches. So now, instead of looking at any area ratio stuff, in fact, ignoring this one now completely, I can now just look at the area of this by doing base times height. Area is 6 times 4, which once again is 24 square inches. So 3 or so different ways of doing that problem, all based on the concept of it. If we have any other area ratio problems, I'll be sure to cover and such. Yes, here's another one. Okay, find the similarity ratio and the ratio of perimeters for each pair of similar figures. All right, this time you have 2 parallelograms of areas 18 and 32 square inches. Now I'm not going to officially draw these in such a way that they measure up perfectly, but I'll just draw a smaller and larger one to get the concept down one more time. Here's the one that's maybe 18 square inches. This one is, let's say that one's 32 square inches, sure. Okay, so that is some sort of base times height. Now they're not asking you to find the perimeter. They're not asking you to find any one side length. By the way, you can't do that. You don't have enough information for it. But what you can do is compare one side length to the other, A to B. Also, I was mentioning stuff about how lengths compare as long as they're corresponding. Well, a perimeter is a length. It's a length of all 4 sides added together. So whatever I get for similarity ratio, it's also going to be the perimeter ratio. Now the area ratio is not the same thing. If I do it from small to large, it's going to be 18 square inches over 32 square inches. It's best that you probably reduce this fraction top and bottom divides by 2, you're going to get 9/16. Now you don't need the square inches here as far as ratio. You're comparing the same thing. So 9/16 is any sort of area in any sort of measurement. It could be square yards or anything like that. So 9/16 is the area ratio. Now the similarity ratio is not 9/16. Similarity ratio is the square root of 9/16. If you square similarity ratio to get area ratio, then you square root area ratio to get similarity ratio. Square root of 9 over square root of 16 is 3/4. Now 3/4 is not the same number as 9/16. 3/4 is 0.75, right? 75%, 1/75% of the other. 9/16 is just a little over 50%. You know, because you know that 8/16 is 50%. So now we can use, well, I'm sorry, we don't have to set anything else up. That's it. Now that does not mean that A is 3 and B is 4. Furthermore, we don't know what units they would be if so. That does mean if A was 3 units, B would be 4 units. If A was 30 units, B would be 40 units. If A was 60 units, B would be 80 units. So that's how the measurement goes. And same with the perimeter and everything else. So we just found similarity ratio and perimeter ratio is the exact same. So similarity ratio from small to large. Well, actually, did they ask us? Just says find it. So from small to large, I'd write 3/4. And ratio of perimeter is also 3/4. However, the small one compares, the larger one is 4/3 that amount, about 33% larger. Not in terms of area. In terms of area, it's 16/9 larger, almost twice as large. Remember that. Number 15, find the area of each triangle, give answers to the nearest tenth. All right, obviously we're just looking at one triangle here. All right, 2 concepts to keep in mind. First one is through a memorization tactic. Sure, have some fun with that. If you have any triangle and you know the lengths of any 2 sides in that triangle and you also happen to know the angle measure that's in between them, let's call it theta, then you can find the area of that triangle by taking half of the product A and B and multiplying that by the sine of that angle, theta. Okay. Now, that is not how I will be doing this problem. I mean, you'll see how it ties in the same way, but I will not be actually calculating this problem with that in mind. Instead, I'll just be doing this a little more conventionally, is all I want to say with that. Okay, so you have a couple of options in how you want to do this problem. Now, what I want to do is draw an altitude from any one vertex down to any side length. Maybe I'll do this problem multiple times here. This is 76 degrees, right? Let me just redraw this triangle a little bigger so I can use it multiple times. Obviously not drawn to scale, that's okay. But this guy down here is 76 degrees. Okay, this is 12 millimeters, 26 millimeters. If I decided to draw an altitude from this vertex down here, no, I will not bisect this 26 into 13 and 13. However, what I need to do is to get the area of this triangle. I need to do some sort of 1/2 base times height. I could use 26 as my base, and h, that would be perpendicular to it right here, I can find by using trigonometry, and then I'd be able to find out my area. So let's go ahead and do that. If this is a right triangle here, I have an angle, I have the side opposite of it, and I have the hypotenuse. This is going to be a sine problem. So if I do sine of 76 degrees, that's going to be equal to h over 12, like that. So what that allows me to do is solve for h. Now I'm going to go ahead and not round an answer early when I calculate it. Multiply both sides by 12. You get h equals 12 times the sine of 76 degrees. That's an exact value for this height right here. So if I want to find the area of this triangle then, it's going to be 1/2 base times height. 1/2 26 times 12 sine of 76 degrees. Okay. And if I wanted to calculate that, that would be, let's see, 13 times 12. I should know what 13 times 12 is. Times sine of 76. Make sure your calculator's in degrees if you're going to be using sine. Round it to the nearest tenth. It's about 151.3, I was about to say degrees, square millimeters. That's rounded to the nearest tenth. Now, I didn't round until the very end. Notice I'm not rounding this number beforehand, before I multiply it by 26 and then take half of it. All right, that's one way of doing that problem, meaning finding that particular height right there. What if I wanted to find another height? What if instead I was keen on finding, say, this height here? Okay, well, that's fine, because this will be my new height, and this will be my base now, 12. And if you look this way, like you can't see which way I'm looking. If you tilt your head, I guess, to the left very fully, you can see a right triangle, 2 legs, and hypotenuse. Hypotenuse here, in this case, is 26. So my option here with this one is, if you take a look, we have height, 26. Now this length is not 12. Don't be too distracted by, this 12 is this whole thing here, not just this small part. And I don't know what that small part is. So let's discard the 12 just for a second so you're not too confused by it. We're going to use sine of 76 because we have opposite over hypotenuse. So the sine of 76 degrees equals h over 26. So h equals 26 times the sine of 76 degrees. Okay. Multiplying that now, okay, now here's where the 12 comes into play. 12 now acts as the base of this triangle because I'm making the perpendicular one right here height. Well, I'm making that the height. So the area of this triangle is 1/2 base 12 times height. And if you calculated that, you'd also get 151.3. Now, I've made mention of this guy over here, this AB sine of theta, 1/2 AB sine of theta right here. If I actually looked at the original triangle, if I called this A, I called this B, and I called this theta, then I would do, the area would be 1/2, 12, 26, sine of 76. Okay, I want you to look at the different times we've done this answer so far. Look at the black one. 1/2 times 26 times 12 times the sine of 76. 1/2 times 12 times 26 times the sine of 76. 1/2, 12 times 26 times the sine of 76. All right, this one's the exact same thing. It's just 12 and 26 were multiplied at a second, or in a different order. So all of these give you the same thing. That's why this theorem is what it is, the way that you break up this thing to make it work in such a way that, it's helpful to you. So all of these give you this answer. All roads lead back to 151.3 square millimeters. That's the area of this triangle. I did it a few different ways. This is one way you may use all on its own if you'd like. You just have to know when it's used, and you have to make sure you use it right. And you have to substitute it right as well. Find the perimeter and area of each regular polygon to the nearest tenth. Okay. So I got an equilateral triangle here. They call it a regular polygon. The radius is 4 meters. Let's go with central angle talk. I'm pretty, I focus on that for the most part in the beginning of these problems. I rarely don't do that. The central angle of a triangle is 360 divided by 6. That's 120 degrees. So half of that, as this apothem here comes in and bisects the angle, that makes this 60 degrees right here. As the apothem is an altitude, as you can see, it makes this a 30, 60, 90 right triangle. So 4 represents the hypotenuse of this in this 30, 60, 90. And the side opposite 30 then should be half that much. So half of 4 is 2 meters. So your apothem right there is 2 meters. Okay. This side, if this unknown right here, is root 3 times larger than this 2. So this here is 2 root 3, which means the entire triangle bottom is double that, which is 4 root 3. So the perimeter is 3 times that amount, which is 12 root 3 meters. So now I have my apothem, I have my perimeter, and I can find the area of this entire triangle in one calculation by doing 1/2 AP. I'm going to go ahead and do that. 1/2 apothem, 2 times perimeter. Half of 2 is 1. 1 times 12 root 3 is 12 root 3. So 12 root 3 square meters. Second way of doing this problem, although it's not, it's definitely not a conventional way. I don't know if I ever talk or teach about this one in class here. I've talked to a couple students about it. But let's say you got this 2 root 3 right here. You know, let's say you got this 4 root 3, this whole thing down here. Okay, well this is 4, because this is a radius. This goes from center to a vertex. Well, this length here goes from center to vertex as well. See that? This length is 4 meters as well. Now this length, this apothem, I believe was 2. So this entire length, this can represent the height of the triangle at large. Meaning I'm referring now to the actual entire height right here. So I can find the area of this triangle by using 1/2 base times height. If I know that my base length is 4 root 3 and my height is 4 plus 2, which is 6 meters. So my area is 1/2 base, 4 root 3 times height. Half of 4 is 2. 2 times 6 is 12. That'll end up giving you 12 root 3 square meters. Now they did ask us to round to the nearest tenth. I want to make sure I answer the question that is asked there. 12 times the square root of 3 is about 20.8 square meters. And there's the area of your triangle in 2 different ways. You can also take the area of this one triangle, as we've done before, and multiply it by 3. Okay, a regular stop sign, a regular octagon right here, has a radius of 10 meters, and now we have to find out, you know, 1/2 AP. I'll just do it the 1/2 AP way this time only. Even though, you know, you can see that this is like a trapezoid here and a rectangle. No, I'll avoid doing that. You know what? Actually, that does sound fun. I'll consider it. I will consider it. Let's do both. I'm a math geek. Let's do both of them right now. Okay, but they still involve you having to do the same stuff. Like, let's start off with a central angle. In an octagon, 360 divided by 8 is 45 degrees. That's what the entire central angle is. Half of 45 degrees is not your favorite number in the world. It is 22.5 degrees. Right there. 22.5. Let me redraw this right triangle a little bigger here, which apparently is a lot bigger. 22.5 sits on top, a right angle sits on bottom, 10 is the hypotenuse. We neither know the apothem nor this unknown side length of the right triangle, x. We may use trig for that in 2 ways. To solve for the apothem, we're going to have to do cosine of 22.5, because that'll be apothem over 10. Okay, so the apothem is 10 times the cosine of 22.5. Now, I dare not average or round off what this apothem value is. I'm going to keep it as 10 times the cosine of 25, or 22.5. Okay. The x value here, you could solve using Pythagorean theorem, but I'm not really in the way of doing x squared plus 10 times cosine 22.5 quantity squared equals 10 squared. I'm going to go ahead and do another trig value again with 22.5, x, and 10. Now I'm going to use sine. So the sine of 22.5 equals x over 10. So x equals the sine of 10 times the sine of 22.5. So that goes there. Now I know, these are big numbers, and really they are. Like both of them are doing 22.5. They're both sine and cosine. Gosh, as an exact answer, this will not look good, even for me. I don't like the look of them, but I do appreciate the fact that it's as exact as it needs to be. So this is x. So this whole thing here is 2x, which is the length of every one side. So 2x is 20 times the sine of 22.5. Okay. So options. I can take the area of this one triangle and multiply it by 8. But I can keep and stick with the apothem times perimeter stuff. The perimeter is 8 times this amount, right? Because there are 8 sides, so that's going to be 160 times the sine of 22.5 degrees. Right? So now I have apothem, I have perimeter. I'm going to do area equals 1/2 AP. So it's 1/2. Apothem is 10 times the cosine of 22.5. Perimeter is 160 times the sine of 22.5. The best looking clean answer, or the best simplest exact answer I could write, I'll take half of 160, which is 80, multiply 80 by 10, that's 800. I'm going to go ahead and write the sine first because we're kind of used to seeing the sine before cosine. Sine of 22.5 times the cosine of 22.5. That's an exact area right there. Not a very good looking one. Let's go ahead and round this. 800 times the sine 22.5 times the cosine 22.5 gives me approximately 282.8. I was about to say degrees. I'm caught up on degrees now. What are the units here? Meters. Square meters. There's the area of your entire regular octagon. Now, I wanted to have some fun with this one because, you know what? We didn't talk about area of trapezoid. I might as well do an area of trapezoid practice problem with you. And here's how I'm going to do it. It's going to take a while. Here I have a trapezoid. And as this is a regular octagon, this trapezoid right here is congruent to it. Okay? And then I have inside here a rectangle. If I add up these three areas here, I should be getting the same area out as I had before. Now there are some pieces of information that I need that I had last time, like one I just erased, this 10 cosine 22.5. And I also need this 2x right here. All right, let's take the areas of individual parts. And to do this, I need as much room as possible. I'm going to get rid of this triangle stuff over here. I just want to confirm and show you how many different ways you can work around a problem. There's no memorization needed until or unless there's limited amounts that are needed. And you can do it with just trapezoids and rectangles as long as you know how to work your way to this stuff here. So, first of all, rectangle area in purple. All right, area of a rectangle is base times height. Okay, the base is 2x, which apparently is 20 times the sine of 22.5. Okay, the height right here is 1 apothem plus another apothem. It's 10 cosine 22.5 plus 10 cosine 22.5, which is 20 cosine 22.5. So total, your area of the rectangle is 20 sine 22.5 plus, not plus, times 20 cosine 22.5, which is 400 times sine of 22.5 cosine 22.5. Okay, so there's that. Okay, the next thing is to take the area of both these trapezoids here. Now I'm going to kind of draw this trapezoid so it's kind of facing a more normal trapezoid way that we tend to do more like that. Okay, the area of a trapezoid is averaging your bases and multiplying that by your height. Okay, now we know that this base length right here, let's call, if this is B1 and B2, here's B1 and B2, we know that B2 right here is the same as the height of that rectangle. So it's 20 times cosine of 22.5. So B2 is 20 cosine 22.5. Yeah, see why I was thinking about, maybe I shouldn't do it. That's okay. I want to have some fun with this here. Oh boy, I can't move that too far. Trying to get these out of the way. B1 is the side length of this octagon. So look, this is 2x, this is 2x, this is 2x. It's a regular octagon. So B1, base 1, is, excuse me, side of 20 times the sine of 22.5. So I'm going to average those bases in a moment here. I just need to get myself some room. You know, I really need to move some stuff over. Maybe even delete some old things that I don't need to use anymore. Okay, the height. This is where stuff gets a little bit harder. Okay, the height is this perpendicular distance right here, the distance between these two. So what you have to now pick up on and recognize is what any of these angles are here, this one or this one. Don't just assume it's a 45, 45, 90. It might be, okay? I mean, I already know what it is, but don't assume that it is just because. You have to know how interior angles work in a regular octagon. Furthermore, you have to understand this is 90 degrees, so whatever the interior angle is, you subtract 90 from it. So another practice thing that we can work on with this instead of just area of trapezoid is how you find the interior angle measure of any regular polygon. So the interior angle sum, if I were to call it D, that is 180 times the number of sides minus 2, n minus 2. So 180 times 6, 360, 720, 1080. So if I added up all the interior angles together, I get 1080. There are 8 interior angles here. They are all congruent. So if I find I, I'm going to take, not 180, I'm going to take 1080 and divide it by 8. And I believe I already know what it is, but I'm going to calculate it just in case I have something forgotten here. Okay, it's 135 degrees. So each interior angle measures 135 degrees. If that's the case, then so is this one right here. So the one that we were looking at is, with this rectangle, 135 is the sum of a 90-degree angle plus what? Well, guess what? That is 45. So you might have lucked out a little bit here. We got a 45-degree angle right there. All right. So that's 45 degrees. This length right here is one that we know. That's one of the side lengths. This side length right here is 20 times the sine of 22.5 degrees. Gosh, if you know why this thing is long, why this thing's going to be long now, this is going to be why. Now, this is a 45, 45, 90 triangle. However, I think it would probably not be helpful to think of this as a 45, 45, 90 in the sense of using a special triangle, because you're going to be dividing by root 2 then, and you're going to use trig with root 2. I'd rather use sine as often as I possibly can here. So I have 45, 45, 90. I have 20 times the sine of 22.5 as the hypotenuse, and I have an unknown height here that I need to get. So I'm going to go ahead and just use sine. The sine of 45 is going to be h over 20 times sine of 22.5. Sine of 45 equals, at least this way I have sine twice, 20 sine of 22.5 right there. So h equals the sine, jeez, I don't know if this has ended up, ultimately if this is going to be worth it. H is 20 times the sine of 45 times the sine of 22.5 degrees right there. And I am a little rusty on my pre-calc, so if there's a way that you can multiply two things with sine, even though they have different angle measures, I know one is more than the other. I believe there is a way, but it's not going to help it become much cleaner than that is right now. So I'm going to keep it like that. Actually, I take that back. I'm not going to, because I want to make it look like this one here in the end. Okay, here's what I'm going to do. New thing that you've never known before. This is so confusing. Skip on. Ignore this problem. I'm doing this for my own good health. All right, there's this idea here that if you take the sine of 2 theta, that is equal to 2 times the sine of theta times the cosine of theta. So sine of 45 is the sine of 20, is the sine of 2, hang on, it's the sine of 2 times 22.5. So this should equal 2 times the sine of 25, or 22.5 times the cosine of 22.5. So that sine of 45 right there, I'm going to change into that, which means that 2 is going to multiply with this 20, which means that's going to be a 40. Okay? So h is going to be equal to 40 times the sine of 22.5 times the cosine of 22.5 times the sine of 22.5. There's another one. Okay? So h now combined, there are 2 sine of 22.5s right there. So we're going to square those. So h is 40 times sine squared of 22.5 times cosine of 22.5. 22.5. See, the problem is I'm not helping anyone unless you're a calculus student here. So there's h. So to find the area of one of these trapezoids here, it's going to be 1/2 averaging these bases here. I still haven't done that for you. The average of the bases here, base average, is 1/2 b1 plus b2. So it's going to be half of 20 sine of 22.5 plus 20 cosine 22.5. So that's going to be 10 sine 22.5 times 10 plus 10 cosine 22.5. There we go. So this average of our bases times our height times 1/2 will give us the final result of the area of one trapezoid, and we're going to double that amount. So the area of one trapezoid is 1/2 base average. No, oh, wait, one second, I'm sorry. We already did the base average part. Average of the bases multiplied by the height, right? So I'm just going to take this and multiply it by the height. 10 sine of 22.5 plus 10 cosine of 22.5 times 40 sine squared of 22.5 times cosine of 22.5. Okay, that's the area of one of these things right here. So if I kind of combine that a little bit, if I multiply it by 2 as well, let's see if I can do all of this in one step here. The area of both trapezoids is going to be 20 sine, 20 cosine times 40 this. So let's distribute this all as best as I can here. It's going to be 800 sine, hang on, 2 to a 20, 2 to a 20. Plus times 800 sine cubed 22.5 times cosine of 22.5 plus 800 sine squared of 22.5 times cosine squared of 22.5. There we go. All right, looks like I can factor out 800 sine squared, sine squared of 22.5. Well, you know what? Well, factoring it out would defeat the purpose of what I was doing here before. So I'll leave it like that. Okay, now I'm going to add this for the area of my entire octagon. That's not an octagon, I know. But it's equal to this number plus, oh yeah, let's go ahead and factor out that 800. 800 sine squared 22.5 times cosine of 22.5. And I'm left with, inside here, a sine of 22.5 plus a cosine of 22.5. Okay, now I'm going to add that with the area of my rectangle, 400 sine of 22.5 cosine 22.5. 400 sine 22.5 cosine 22.5. Okay. All right, so I'm going to go ahead and add all this together. Like, I know there's more I could factor out here, but I'm going to avoid doing that. Let's see if I'm even close to what I got here. 800 sine 22.5 quantity squared times cosine of 22.5 times sine of 22.5 plus cosine of 22.5 plus, oh, close parentheses, plus 400 sine of 22.5 cosine of 22.5. I get an answer of 282.84. 282 points, so I'll put 0.8 square meters. Now, what was my answer up here? Where is my answer? Ah, 282.8. So I got the same answer. Oh, all right. So I still know some of my stuff here. So there's another way to do this problem. Lesson here, kids, is be appreciative of the formulas they give you and don't work around this any sort of different way. I did this not for your knowledge. I actually hope that you skip this problem. This was just me working it around a different way. I thought it was actually going to be quicker and cleaner, but that height ended up being a problem. The trapezoids ended up being a big problem. So lesson here is use 1/2 AP as needed, or use triangles as needed. That's why they are the better of all things here. There was probably a cleaner way to factor this, and in fact, I'm sure there's a way I can clean it up and make it look like this, but I got to be a little more versed in my trig again to make it happen, because I'm sure I could have gotten it back to that. But hey, I got the same answer. I left nothing out of place here. Okay, now that we're in a way new different part of this, I think this is section 10.6 now. Find the measure of each arc in circle P. I was only asked to find the measure of arc CD. All right, this problem's going to be a little shorter than the last problem I just did. Okay, arc CD is the same as this central angle measure. Let's call it central angle measure X. Here's what you know. You know that this chord, and I can use that word now because now you know what it is. You know that this chord is running through the center. That makes this a diameter. If this is a diameter, that makes this whole thing right here a central angle of 180 degrees. It's half of a full circle. It's a semicircle. So I know that if I add 128 degrees with X, I'm going to get 180. Subtract 128, I get X equals 52. If X is 52, then the measure of arc CD is also 52 degrees. Okay, now they did not ask us for the length of arc CD. They asked us for the measure of it. If they asked us to find the length, we'd be out of luck because we don't know any side lengths here, any radii, any circumference. We don't know anything else about it. So we can't get any length out of this even if we wanted to. Find the length of each arc. Okay, so this is a length problem. Here you go. Find the length of each arc shown in red. Leave your answer in terms of pi. Sounds good. Okay. Let's first talk on the angles here because I want to look at this measure, this angle right here. If this is 60, central angle here is also 60. We talked about this chord being a diameter, which means this adds to 180. You know 60 and 120 are supplementary, so this angle right here is 120 degrees, which makes this arc 120 degrees. So what I'm going to do is find out what fraction 120 degrees is out of 360, out of the entire thing. Whatever that fraction is, this arc is that fraction of this circle's entire circumference. Okay, so first thing I'm going to do here is my diameter is 24 feet. I'm going to find the circumference by doing diameter times pi. So that's going to be 24 pi feet. Not square feet, just feet. Okay, that's the circumference of the circle. So to find out the measure of this one arc of the circle, I'm going to go ahead and say, well, 120 out of 360 is equivalent to that amount. Normally I multiply it by it. Yeah, I guess I will. I was going to say some people do proportions. Okay, but I wouldn't multiply straight up right now. 120 over 360 is 1/3. Hey, hang on a second. Length of arc equals. This equals 1/3. So we're going to do 1/3 of 24 pi, which is 8 pi centimeters exactly. They said leave your answer in terms of pi. There it is. If I round it to the nearest tenth, I know the number is a little bit more, not centimeters, what am I saying? Feet. I know that the answer is a little more than 24 feet because pi is 3.14. 8 times 3 is 24. Find the area of each shaded segment, round your answer to the nearest tenth. Okay, I don't believe these were necessarily homework problems that you had, but they were requested of me to do, so I'll go ahead and do them for you either way. We got to find the area of this shaded segment right here for this one. Okay, it's going to be required for us to find two things first. The area of this sector, and then the area of this triangle. If I subtract the triangle from the sector, I will get this segment right here. Now the endpoints here measure at an arc or central angle of 120 degrees. So we're going to do the same thing as we did last time. We're going to take 120 out of 360, which is 1/3. we're going to apply that to the area of the entire circle. So the area of the circle is pi times the radius 6 squared. So that's 36 pi square centimeters. The area of the sector is going to be 120 over 360, which is 1/3 36 pi. So that's 12 pi square centimeters. Okay? So that's this. This is 12 pi. What I need next is the area of this triangle. So I'm going to redraw this triangle, a little upright. It'll help. Okay. Redrawn upright here, we have radii that are congruent. So this is 6 centimeters. This is 6 centimeters. You have options on how to do this one. You can do the 1/2 AB sine theta. By the way, this angle here is 120 degrees. You do 1/2 AB sine theta, but let me do that altitude thing one more time because I want to talk about how this altitude bisects this isosceles triangle. And by talking about it, all I have to say is this altitude bisects this triangle. And it bisects the side down here, and it's perpendicular, obviously. That's the point of an altitude. So if it bisects this angle into 60 degrees, we're looking at a 30, 60, 90 triangle. To find the area of this triangle, I can call this the height, if I call this one the base, and I got to find the lengths of both. The hypotenuse is 6. H is going to be half of it as its opposite, 30. H is 3 centimeters. So this small length right here, not the whole base side, but half of it, is going to be √3 times larger than the height. That's 3√3. So your base right here is 6√3 centimeters. So the area of your triangle is 1/2 6√3 times height. So base times height. Half of 6 is 3. 3 times 3 is 9. So we get 9√3 square centimeters right there. So that's the area of this whole triangle right here. Okay. An alternative way of doing it and or writing it is using 1/2 AB sine theta. Now remember, I did not actually use sine here, even though I could have, but I did not. In doing so, if I do 1/2 AB sine theta, it would be 1/2 6 times 6 times sine of 120. So I avoided going that route there, but this is the exact same thing. 18 sine of 120 apparently is the exact same thing as 9√3. So you can connect those two, try and calculate them. They should be the same. Both the same areas, either one or the other. We have to still find this by subtracting this value from 12 pi. So the area of the segment is 12 pi, the area of the sector, minus 9√3. That's in square centimeters. Rounded to the nearest tenth, as they asked us to do. Let's go ahead and figure that one out. 12 pi minus 9√3 is about 22.1 square centimeters. Okay. There's another way of finding the area of this triangle. I actually did it the other day when I was in class. I went and found this height here and I multiplied it with this. I did 1/2 base times height, and I found out this height by saying this is 120. Oh, this is 60. This is 6, and a 30, 60, 90, blah, 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 blah. So I found out that height doing the exact same thing, got an area back to 9√3, I suppose. But again, multiple ways to do a problem. The reason why I offer so many is to show that you're not confined to one way, and maybe I'm not catering to just one person by doing it a certain way compared to another. Okay, the area of this shaded region here, they give you, I don't really know what they give you. I assume they're giving you the arc measure, which is 60 degrees, which means the central angle here is also 60. Vertical angles are congruent, so this angle is also 60 degrees as well, so this arc is also 60 degrees. Okay, we got a radius of 6 meters here. This time I will shorten up the whole stuff. This time I will do 1/2 AB sine of theta when I find the area of the triangle. Just shorten it up and say, hey, let's use this one this time. But first I gotta find the measure, the area of this sector right here. And that'll be by first doing pi r squared for the area of the circle, It's once again going to be 36 pi, only this time it's going to be meters, not centimeters. So they're not exactly the same. In fact, they're not even close, technically. The area of the sector is going to be 60 out of 360 this time, and multiplying that by 36 pi. Well, 60 out of 360 is 1/6, and 1/6 of 36 is 6. So the area of the sector is 6 pi, this guy right here. Okay. The area of the triangle, as I just said that I'd do shorter this time, if 6 and 6 are these two A and B's here, and theta is 60, it's going to be 1/2 A, B, sine of theta, which is going to be half of 36, which is 18, times sine of 60. There's the area of the triangle. Here's the area of the sector. Let's subtract. Let's do area of sector minus area of triangle to get the area of the segment. It's going to be 6 pi minus 18 sine of 60. And I know what you're thinking, like you're taking a look at that and saying, isn't 18 sine of 60 bigger? I mean, it only has bigger numbers and there are more of them. Yeah, but no, it's not. Remember, pi is also a number. Sine of 60 is less than 1. No, it's smaller. So 6 pi, rounded to the nearest tenth here. By the way, this is square meters. 6 pi minus 18 times the sine of 60. Be hilarious if I wasn't actually in degrees this whole time. And it's not much larger, apparently. It's going to be 3.3 square meters, approximately. Okay. But remember, that's that small segment right there. That's it. And that makes sense that it's really that small, too. Okay, now we're dealing with chapter 11 here. Find the surface area of this pyramid to the nearest whole number. Okay, here's what we got. A hexagonal pyramid. Now the pyramid goes straight upright, which means the slant height is congruent all the way around, this one of 8 meters. We have some given information down here, probably more than they needed to give you, okay? In the sense that they could have just given you the apothem and said, here kid, you find out the rest. That's, they're being very nice for you by doing this here. I'm going to go ahead and draw the net for this thing. Okay, and in doing so, I have that first part right there. I'm going to go ahead and connect this here to it. Make it look as authentic as I can. Okay, let's say that's one of them. All right, and drawing the net, so basically finding the surface area is finding the area of all of these triangles, all 6 of these triangles with this one hexagon. It's one regular hexagon. So there's 6 that open up this way. Now this is the way that I'd recommend that you do it. Okay, in that you don't unfold from the triangles like you would a prism, because it would end up looking like the cone-shaped thing, which is already enough of a bother for people. So I'd instead go about it some other way. Oops, that didn't work. There we go. 5 and one more. Flip up, down. Okay, there we go. There's our net. Beautiful. What they give us here, this slant height, as you unfold this is the slant height. It's also the height of your triangles here. So this is 8 meters. They give you the length of all the sides of this regular hexagon here. Again, they were very nice of doing that with giving you the apothem. They did not need to give you both here. So you don't have to do too much with this. You've already gotten all the information you need to calculate these things, meaning I don't need to be building special triangles around anywhere anytime soon. This is 2√3, because surface area of a pyramid is all about the lateral area, the area of all the triangles, plus the area of your one base. All right, let me do the area of the base first, because we've just been doing area of regular hexagons. Let's keep at it. Area of the base is 1/2 apothem times perimeter. Perimeter is just 4 times 6, 24. We already have the apothem, 2√3. So the area of the base is 1/2 apothem times perimeter. And the reason why I kept saying they're nice to have gotten you that 4 here is because you could have found it by doing your central angle nonsense and finding out that this was 2, so double that was 4, all that. We could have done that. It looks like they helped us refrain from it though. So 24 root 3 square meters. There's the area of the one base. Okay, to find the lateral area, the area of all 6 triangles, you can take the area of one triangle and multiply it by 6. 1/2 base times height, which is 16 square meters. And then your lateral area, therefore, will be 16 times 6, which is 96. Okay, or use the formula that you've been ingrained with, which is 1/2 perimeter times slant height. Now, height of triangle is slant height of pyramid, which is still 8. So lateral area in total is 1/2 perimeter, which we know is 24 already, times slant height, which we know is 8. Half of 24 is 12. 12 times 8 is 96. So either way, you still get there. So we're pretty set with that. So we got 96 there. Base area of 24 root 3. They do ask us to round to the nearest whole number. First, I'm going to write this out in full. Total surface area, 96 plus 24 root 3 square meters. There's the actual, or there's the exact one, the approximated one. By the way, I can't add this 96 with this 24 because the 24 is being multiplied by a root 3. So it's not going to be the same as 120 root 3. This rounds to 137.6. Nearest whole number, 138 square meters. Just for good measure, no pun intended, if you wanted to know what 120 root 3 was, it's 207.8, so about 208 square meters. So obviously this is not the same thing as 120 root 3. Keeping that in mind for those who have made that mistake in the past. Here, before I finish here, I want to see how many problems I have left. I have 3 more problems, 7, 12, and 16, okay? Just making sure you know where we're at. So 3 more. It's a word problem. The original height of the pyramid built for Khafre, or something like that, next to the Great Pyramid was about 471 feet. Each side of its square base, so pyramid with square base, square pyramid, was about 708 feet. What is the lateral area to the nearest square foot of a pyramid with those dimensions? So, square pyramid, might look a little bit like this here. In the end of time, there was a man who knew the way. And that's not looking too good. Let's extend that a little more. There we go. All right. Pretty nice. Now, they mentioned height. Okay. Last time, what did I use? Slant height. They're mentioning height. That is from center up to the crown. This height here is 471 feet, not the slant height, which means we don't know the slant height yet. They didn't tell us, and we need it because we're doing well, not surface area, but we're doing lateral area, which uses slant height. So we got to find, we got to find this guy right here. Still, it's the one that goes right, it goes perpendicular to it, and because it's an isosceles triangle, it goes right down the middle. That's L. Now, what we also know here is the side length is 708 feet. Now, although I do not need to find the area of my base, I'm going to draw this base from top down so you can see what it is I'm about to do. The center goes right here. We know we're going out to a slant height this way. That's going to look like that, right? So we got to find out what this length is here to start to find out the slant height. And as we know, in a square here, the apothem is actually half of this guy right here. So half of 708 is 359. No, 354. Yeah, 354 feet. So that is that length right there. Now, these are weird numbers. I wonder what L is going to be. I don't know if it's going to be an integer or not. They do say to the nearest square foot, so I'm guessing we're going to get some decimal practice here. So how do we find it? Oh, Pythagorean theorem. L is the hypotenuse of these two guys here, 471 squared plus 354 squared equals L squared. 471 squared is 221,841 plus 354 quantity squared. We're going to get L squared as 347,157. Take the square root of both sides. L is, oops, hang on, 589.2003055. Basically, not a whole number. So, what is it really? It's really the square root of 347,157. Sorry, I know it's really close to 589, but if we decide to use that and we round too early before we do all our other stuff, we're going to be wrong in the end in some way. Now, this might have some perfect square factors in it, but I'm not going to bother with that. This is large enough as is. The other one's going to be plenty large as well. Okay, so we need to find the lateral area. So we need to find the area of all four of these triangles, basically. This time I'm just going to find the area of one triangle, and I'm going to go ahead and multiply it by 4. Okay. So the area of one triangle is 1/2. Base length is 708. The height, as we know, is square root of 347,157. And then I'm going to take all of that and multiply it by 4. How about that? So 4 times 1/2 is 2. 2 times 708 is 1,416. It's probably the year this was being done, right? Actually, it's probably closer to 708. Root 347157. Now that is the, I guess I should put this the lateral area then, because that was the area of one triangle times 4. So this is the lateral area. So that's the exact number. That's square feet. Rounded to the nearest whole number, multiply the square root of 347,157 by 1,416. It's going to be about 834,308 square feet. Not exactly, but about. Just so you know, if instead I changed my number from 589.200 whatever to 589, my answer would be 834,024. I would have been about 280. I would have been 283 square feet off. Okay. If I did 589.2 times 1416, well, I would have gotten 834,307 square feet. You're like, ooh, 1 square foot off. Well, guess what? If this was a multiple choice final and there was this option and there was this option and you circled this one, you would have been wrong. So, you know, there's that. Anyway, yeah, so just with rounding, don't do it till the very end, right? Use that exact answer as needed. Okay, 2 more. The surface areas of 2 similar figures are given. The volume of the larger figure is given. Find the volume of the smaller figure. So we talked about ratio of area already, and I'm not going to break it down into a whole nother teaching again. We've done the ratio of volume in so many ways, including, you know, the cone. And by the way, these figures might be cones. You don't know. But like the cone of this one. And if it's like, sir, pour me wine with, you know, this height. I know I shouldn't be talking about wine to students. And they... pour me half a glass, right? And he pours you this half of this glass, but he pours it in terms of half the height because whatever this is twice as much. Okay, the problem is you only drank 1/8 of this entire volume. Okay, only 1/8. In other words, you can take 8 of these and fit it into the entire glass. So that's how ratio of volume works. You're going to cube similarity ratio. All right. So before I do anything else, let me first write those things out. If the similarity ratio is A over B, then the area ratio, now that's comparing any sort of area, including surface areas. It's A squared over B squared, and the volume ratio is A cubed over B cubed. Okay, so I have area ratio. right here. I'm going to compare these two. Let's do small to large. I'm used to doing that recently. So the area ratio here is the ratio of these two surface areas. Because they're similar figures, and because we're corresponding to the same thing, I'm going to be able to compare them, and I can call that area ratio. That number can possibly be reduced. Well, it could definitely be reduced, even numbers here. But I wonder how much. Let's see if my calculator can help me out here. Okay, so it goes out to 0.1111, which I know is 1/9. So area ratio reduces here to 1/9. To find the volume ratio, notice I need to get from a squared over b squared to a cubed over b cubed. One step is kind of hard to do that with. Instead, let's do this. Let's take the square root of these, and then let's go ahead and cube them. So let's find similarity ratio based on area ratio. That's going to be taking the square root of 1/9. Square root of 1 over square root of 9 is 1/3. Okay? Which means basically whatever two objects I'm looking at, one has triple the lengths of the other. Okay. Volume ratio now is taking the similarity ratio and cubing it. So 1 cubed over 3 cubed is 1/27. Okay, this ratio is the one that I'm going to use when setting up these two volumes. They give me the volume of the larger figure, which means the volume of the larger figure is 27 times the volume of the smaller figure, which is what they're asking me to find. So in order to do this, I can either take 1/27 of 4860, or just set up the proportion with it. Small to large equals small to large. Okay, cross multiply, all that, whatever. You're going to do 4860 divided by 27 in the end. That becomes exactly 180 cubic meters. So the take-home thing behind this is surface area, let's say these are two different houses, right? And the houses were built for whatever reason. One's a smaller size of the other, one's a larger scale. Or let's say these were two models, like a model of a smaller thing. And not a house, because one's 3 times larger. But, two things that are compared like that. And you need to paint both of them. You need to buy the right amount of paint for this. This one's this much, and this one's this much. All right, awesome. The question is, how much now water could you fill in? Now, I don't know if we're talking about a house anymore. But how much of volume could you fill in one versus the other? Well, this, you need 9 times more the amount of paint for than this. This, you need 27 times the amount of water that you need for this. And this one's 3 times larger in length than this one in every direction. Okay. All right, last one. It's number 17. There are 750 toothpicks in a regular sized box. If a jumbo box is made by doubling all the dimensions of the regularly sized box, how many toothpicks will the jumbo box hold? Here's a box of toothpicks. It's the regular sized one. 750 of them. Now, toothpicks, it's not toothpicks cubed or anything like that. It doesn't have anything there. That doesn't mean this is not a 3-dimensional measurement, right? Toothpicks occupy 3-dimensional space. So if that's the case here, then we're talking about volume ratio. If I want to compare this amount of toothpicks with the amount of toothpicks in a larger box that's like similarly shaped, doubling all the dimensions, okay, then I'm comparing ratios of volumes. So these toothpicks here, let me delete all that. So here's a box of the regular toothpicks, yada yada. And let's go ahead and let's double these lengths. I'm going to take this, change the color, and let's get about double that length there. It's a little bit larger. Now, as I grow this thing, the Smart Notebook program knows how to knows how to grow similarly. So it grew in every direction twice as much. So the question is, that I want to ask you is, how many of these can fit in one of these? And the answer is, you're probably looking at it now. You're like, ooh, 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 ooh. Ooh, I know. I know you know. But let me keep playing with this. assuming I put them all in, that's 8 of them, right? Not that you needed to draw this in your thing, but if you're doubling all the dimensions of the regularly sized toothpick box, then you've made a larger jumbo-sized toothpick box that is 8 times as large, because you can fit 8 of them in there, which means you can fit 8 times the amount of toothpicks in there that you could before. So really, your final answer is just going to be 8 times 750, which I believe is 6,000. Okay. If you were to do it in a more mathematical sense and you didn't have this mindset for it, you'd say, I have the volume ratio right now. This is 750 over some unknown amount. Or I'm sorry, not that I have the volume ratio. I have to compare these two things here. I have the similarity ratio right now as 1 to 2 from small to large. I'm going to double the lengths everywhere. The volume ratio here that I'm going to be using is by cubing this, which is 1 to 8. So whatever size this is 8 times larger. So as you set up that proportion, you get that right there. X equals 8 times 750 as you cross multiply. And I think that's 6,000. Let me calculate that. Yeah, 6,000. So the jumbo box can hold, I've never used 7 toothpicks in my life. I don't know what you'd use all those toothpicks for. Actually, I take that back. In geometry, I did a toothpick bridge project. That was pretty fun, but I didn't use this many. Anyway, it's a lot of toothpicks. So that's the last one. So I'm done. I mean, beyond this is just me closing out. So if there's anything else that you need to look through beyond that, through the scope of this stuff, make sure that you ask away, please, because this is only what was requested and not necessarily everything that's covered on the final. So there's a difference between the two. Furthermore, I do some other stuff that's completely, where is it? That's like this, that's completely outlandish. You can ignore all that, please do. But be ready for pre-calc or calculus when you'd have something like that and they say, find this area this way. Anyway, I had fun doing this. I always do. I hope you can get something out of it as well. Happy studying. Fiend!